When the domain boundaries have been decided, the next step is to create the geometry, and to do that you need a solid model of the domain. It's important to note that for CFD simulation, you need the solid model to represent the fluid region. If you're working with a CAD model, the fluid region can often be extracted from the solid parts, but other times if the flow region is relatively simple, like in the T-junction down here, it might be easier just to create the fluid region from scratch. You next need to consider the possibility of making some simplifications to the geometry. CAD models often contain geometrical details that are important for manufacturing or assembly, but not so important for the flow, like fillets or bolts. These kinds of features can make the process of meshing the geometry more complicated, or they can result in an unnecessarily high number of control volumes in the mesh, which in turn leads to longer calculation times. So as much as possible, you want to plan to remove features like this from the geometry. Symmetry or periodicity in the solution can allow for smaller models or faster runtimes, but you do need to be sure that not only the geometry is symmetric or periodic, but also that the flow and the boundary conditions are too, otherwise you're imposing an unphysical condition on the solution. And finally, sometimes the model might need to be split into more than one piece in order to be able to apply different boundary conditions at different locations, or to define separate domains inside the model, such as porous medium regions or solid regions for conjugate heat transfer. After the geometry has been created, the final pre-processing step is that of creating the mesh. The mesh needs to be created in such a way that the grid points are close enough together to predict regions of high gradients in the flow or temperature fields, and also such that the grid points are close enough to resolve geometric features of interest. There may be cases where you know from engineering experience where gradients will be high, but there may be other cases, and shockwaves are a good example of this, where it might be difficult to predict ahead of time. So if this is the case, you might want to plan to use mesh adaptation so that you can add mesh resolution only where it's necessary. Another decision you need to make is what kind of mesh is most appropriate for your problem, and that's often determined by how complex your geometry is. If the geometry is relatively simple, like the diffuser up here in the upper right, then hexahedral cells are preferable because you end up with a lower cell count for a given mesh resolution, and that means that the solution will run faster. On the other hand, in very complex geometry like the automotive underhood simulation down here, it's probably more efficient to use a tetrahedral mesh. Depending on the geometry, it can sometimes be difficult to mesh the entire domain with a single meshing strategy. If this happens, then sometimes the use of non-conformal interfaces can make meshing a lot easier by allowing optimal meshing strategies to be used in different parts of the domain. Finally, you also need to make sure it's possible to solve the problem on your computer system once the mesh has been created. The amount of memory required per cell depends on what physical models are being used, but a general guideline is that for single-phase flow with heat transfer and a two-equation turbulence model, about 1 gigabyte of RAM is necessary for every 1 million cells in the mesh. If you do problems with multiphase or certain kinds of radiation or combustion models where many additional transport equations need to be solved, then the memory requirements would increase.